Stars, those celestial beacons, appear to us as a shimmering scatter of diamonds against the velvet backdrop of the night sky. Yet behind this serene facade lie raging nuclear reactors, capable of generating enough energy to vaporize Earth countless times over. Their very existence hinges on the production of this colossal energy, which sustains not only their own lives, but also our very being. In the boundless expanse of the universe, nothing is eternal, not even stars. Broadly speaking, they fall into two categories: low-mass and high-mass stars. The dividing line lies at roughly 8 solar masses, and it soon becomes clear why this threshold holds such profound significance. While the life cycles of massive stars are fascinating, our focus here will be on low-mass stars, whose evolution is comparatively straightforward to grasp. Deep within every star, energy is continuously generated through the fusion of hydrogen into helium. Though this process may seem simple at first glance, it is in fact extraordinarily complex, involving numerous stages. Ultimately, 4 protons and other particles fuse to form a single helium nucleus. Each such reaction releases a minuscule amount of energy, but given that this transformation occurs countless times every second in a star's core, the cumulative energy output becomes truly immense, sufficient to sustain the star's luminosity and stability. The rate of hydrogen fusion depends directly on the pressure within the star's core. The denser the star, the more intensely it compresses hydrogen, accelerating fusion. Paradoxically, despite their greater size, massive stars consume their hydrogen fuel far more rapidly than low-mass stars. The less dense a star, the longer its lifespan. In low-density stars, such as cool red dwarfs, the fusion rate is so slow that their lifetimes stretch into almost unimaginable durations. But there's more to it. Red dwarfs fuse hydrogen only in their relatively small cores. Beyond this central region, the gas is in a state of convection. Hot material rises toward the surface, cools, and then sinks back down into the core. This process is crucial. It means that virtually the entire mass of the star becomes available as fuel. Hydrogen and helium circulate throughout the star, rising, cooling, and returning to the core. Although the star cannot fuse helium, the hydrogen that cycles back into the core serves as a continuous supplementary fuel source. Thus, even after vast stretches of time, these stars continue to shine as long as fresh hydrogen reaches their cores. So, just how long do low-mass red dwarfs live? 1 trillion years. Yes, a full trillion. By comparison, the universe itself is less than 14 billion years old. Consequently, the oldest red dwarfs are, in cosmic terms, mere newborns. They have only just begun their journey, and will retain their current appearance for another 990 billion years. Eventually, however, they will exhaust all their fuel. When a star runs out of fuel, its composition becomes pure helium, enriched with heavier elements it contained from its birth. Fusion ceases, and the star begins to cool, a process that itself takes billions of years. Ultimately, it becomes a dead, dark, and frigid stellar remnant, marking the end of its life. At least, that's the accepted theory. But the universe is still far too young for any red dwarf to have reached this stage. These characteristics apply to low-mass stars with roughly 1/3 the Sun's mass. Stars more massive than this, like our Sun, behave differently, as their cores are larger, hotter, and denser. These internal conditions suppress convection within the core itself. Hot material doesn't rise far from the center, and core material remains trapped. Outside the core, these stars do possess a deep and active convective zone, but it doesn't mix with the core's contents. This means Sun-like stars not only burn through their fuel faster than red dwarfs, but also have access to a smaller fraction of their total hydrogen. Depending on their exact mass, their lifespans are far shorter. The Sun, for instance, has a total lifespan of about 12 billion years. Currently, it is roughly 5 billion years old, placing it squarely in the middle of its life. Since the Sun's evolution mirrors that of similar mass stars, let's peer into the distant future. Will our Sun fade away quietly? Since its birth, it has steadily fused hydrogen into helium in its core. This helium, unable to serve as fuel under current conditions, accumulates like ash in a fireplace, gradually increasing the core's density. As gas compresses, its temperature rises, so the Sun's core grows slightly hotter each day. This extra heat radiates outward, warming the Sun's outer layers. Hotter gas shines more brightly, so the Sun is also gradually growing more luminous. This is an extremely slow but relentless process. Since its formation, the Sun's brightness has increased by about 40%, and it won't stop there. Helium continues to build up, and eventually the hydrogen will run out. Without fuel, core fusion will cease. Helium can fuse into carbon, along with trace amounts of oxygen and neon, but only at extremely high temperatures. The Sun's core will never become hot enough for this. Nevertheless, half the Sun's mass continues to press down on the core. Even after fusion stops, the core will keep contracting and heating until it becomes hot enough to ignite hydrogen fusion just outside the core itself. Hydrogen in a shell surrounding the inert helium core will begin to fuse, like lighting a match near a flame. This shell burning will heat the Sun's outer layers, causing the gas to expand. The Sun will swell to roughly twice its current size, entering a phase astronomers call the subgiant stage. Along with growing larger, the Sun will change color. It will emit far more total energy than today, and its surface area will increase dramatically. However, because that energy is spread over a vastly larger area, the energy emitted per square centimeter will actually decrease. Paradoxically, this causes the Sun's surface to cool, and cooler stars appear redder. Thus, the Sun will take on a reddish hue. Meanwhile, the core continues to contract and heat up. Eventually, it becomes so hot that the outer layers expand dramatically, and the Sun swells to 10 to 150 times its current size, becoming a red giant. Red giants are exceptionally luminous, not only because of their immense energy output, but also due to their colossal surface area. When the Sun becomes a red giant, its brightness will increase by a factor of 2,000. This extraordinary luminosity, combined with its vast size, will drastically reduce surface gravity. The outward pressure from radiation will easily overpower the weakened gravitational pull holding the star together. Material from the sun's surface will be flung outward like leaves caught in a hurricane, akin to a supercharged solar wind. At this stage, the sun will lose mass at a rate far exceeding its current output. By the time it reaches the red giant phase, it will have shed about 1/3 of its mass. At a certain point, the core's temperature and pressure will rise enough to ignite helium fusion. Suddenly, helium will fuse into carbon, releasing a tremendous burst of energy. Due to complex physical processes, the core will then expand in a counterintuitive way, absorbing much of this energy. As a result, it will deliver less energy to the outer layers, which will contract. The increased density will raise their temperature, and the sun's color will shift from red to orange. The sun will remain relatively large, about 10 times its current diameter, and shine 20 to 50 times more brightly than today. But then history will repeat itself. Helium will now fuse in the core, and carbon will accumulate like ash. The core will again contract and heat up. This will pump more energy into the outer layers, causing them to expand and cool once more, turning the sun back into a red giant. This time, however, it will be even brighter and larger, and it will shed more than half its remaining mass. Helium fusion will become highly unstable, fluctuating wildly over short timescales. The sun will likely experience a series of massive thermal pulses, powerful eruptions driven by erratic helium fusion, each unleashing colossal energy surges. With every pulse, it will lose more mass. But this marks the approach of its end. The sun's mass will eventually become too low to compress carbon atoms enough for fusion. Carbon will accumulate in the core until helium is exhausted and fusion stops entirely. After that, nothing remains. At this point, the sun will eject all its outer layers, leaving behind only its exposed core, a hot, dense, Earth-sized ember known as a white dwarf. Its fate is sealed. Unable to generate new energy, it will slowly cool and fade over the next 10 billion years. At that stage, we can truly say the sun has died. Yet this isn't the end for all stars. Some stars, more massive than the sun, undergo an additional spectacular phase before their demise. They form what's known as a planetary nebula. This breathtaking phenomenon deserves its own episode, and we'll explore both planetary nebulae and white dwarfs in the next installment. Thus concludes our story of the sun. But what about us? This cosmic drama certainly won't bode well for Earth. Long before the sun becomes a subgiant, our planet will become uninhabitable. By the time the sun enters its red giant phase, Earth will already be scorched and destroyed. Surface temperatures will soar so high they'll melt rock, returning our planet to the molten state it held billions of years ago. And conditions will only worsen. As the sun expands, its outer layers may reach Earth's current orbital distance. Does this mean Earth will be swallowed? Possibly not. Remember, as the sun loses mass during expansion, its gravity weakens. Consequently, Earth's orbit will widen. In the grand scheme of cosmic events, if conditions align favorably, Earth might escape direct engulfment. drifting outward faster than the sun expands. According to the laws of physics, if the sun sheds more than half its mass, its gravitational grip will weaken so much that planets could break free entirely, drifting into interstellar space. Yet this outcome offers little comfort to humanity. Regardless of the exact scenario, Earth's doom is inevitable. Still, there is hope. By that distant era, humanity may have mastered interstellar travel. Earth-like planets in other star systems could then serve as ideal refuges, though these events lie over 1 billion years in the future. The Sun won't enter its subgiant phase until it's about 11 billion years old, more than 6 billion years from now. The first red giant phase will begin after 11.5 billion years, with the second phase unfolding 500 million years later. These are truly immense timescales. The Sun could have avoided this fate had it been more massive. A star 8 times heavier than the Sun possesses enough gravity to compress its carbon core and ignite further fusion, sidestepping the white dwarf endpoint. The fate of massive stars differs significantly and is, in fact, far more explosive than that of low-mass stars. We'll delve into their dramatic life cycles soon, presenting a detailed and captivating account. And while these prospects may seem bleak, hope endures. These processes are an intrinsic part of the universe, natural cycle, and without the life and death of stars, our very existence would be impossible. We should be grateful for what we have. Not only do we witness these cosmic transformations, but we also strive to understand them. Today, we've learned that low-mass stars live extraordinarily long lives, fusing all their hydrogen into helium over trillions of years. In contrast, more massive stars like the Sun have shorter lives. They fuse hydrogen into helium, then into carbon, oxygen, and neon. As this occurs, they expand, grow brighter yet cooler, become red giants, shed much of their mass, expose their cores, and finally cool over millions of years, completing their journey through the grand cosmic cycle.